So now I'm going to do the same inductive type of substitution proof for the recurrence 2t of n over 2, this time using asymptotic notation. I'm going to say plus big O of n, not big theta, because this is simpler. Big O of n on the right-hand side merely means there exists some function f of n such that f of n is going to be less than or equal to some constant times n, which is inside that big O. And of course 0 is less than f of n. And this is only true when n is bigger than some n naught. And we can treat those c and n naughts as input to us, so they're given. This means that our overall recurrence is really saying that t of n is less than or equal to 2tn over 2 plus some constant times n. I mean, that constant comes from the definition of big O, and that less than or equal to sign comes from the definition of big O. And it's not drawn here, but there's an n naught involved that we inherited as well. So we can say that for n greater than n naught, t of n is less than or equal to all that. We want to prove something, and we want to prove that t of n is big O of n log n. And again, from the definition of big O, what this really means is that there exists some constant, let's call this one b, we've already used c, such that t of n is less than or equal to b times n log n. Again, for n greater than some other n naught, we'll call it n naught prime. I won't even draw it here. So our inductive hypothesis, and we're going to use an inductive proof, right? And our inductive hypothesis is that t of n is less than bn log n. Our basis case is to show that for some constant, any constant n, t of n is order 1. And in fact, that's always true. If n is bounded above, for fixed size problems, you can always do a brute force solution, and it's considered O1. We don't even need to do anything for the basis case. So we'll find with big O involved, we just ignore the basis case, really. And instead, we've got t of n is less than or equal to 2 times t of n over 2, plus, remember we had order n, which, again, I'm trying to get rid of those, so I'm going to erase that and draw, it's really plus c times n here on the right-hand side. So we think of big order n as being less than or equal to c times n, and we're bearing in mind that this is for big N. So rewriting this and applying the inductive hypothesis, so we think t of n over 2 is going to be b n log n, or rather b, actually t n over 2 is going to be less than or equal to b times n over 2 times the log of n over 2 plus c times n. And I had to make that less than or equal to because our inductive hypothesis is that t of n over 2 is less than or equal to b times n log n. So since t n over 2 is less than or equal to that, our whole thing here, our whole thing should be less than or equal to that. So, okay, so given that, this whole expression, we can cross out the 2's, being careful not to cross out that n over 2 that's in the argument to the logarithm. And we get the expression bn log n over 2 plus cn. And the log n over 2 is log of n minus log of 2, which is really just log of n minus 1. And distributing that, we get b times n times the log of n plus b times n times minus 1. So it's minus b times n. Plus c times n. So we haven't gotten the exact form that we want yet. So we've got b n log n plus, looks like c minus b times n. And we want to show that that's less than or equal to b times n log n. That's exactly what we want on the right-hand side. But we got this extra stuff here from the previous equation that we don't want to show up. But we get to pick b. That whole less than or equal to sign is going to be true whenever c minus b is positive, because n is positive. So if c minus b is greater than 0, our proof is done. The trick is we get to choose b. C is given. And we can pretend that we know what c is. So we can express b in terms of c. In this case, something simple like letting b equal c will probably work for this proof. So if we choose our b to be the c, then we've actually proved it. We've reproduced exactly that which we aimed to show, which is that t of n is less than or equal to b n log n for some n greater than, in this case, our n naught is going to be the same n naught that came from the original big O. So this is how you do it for big O. It's sort of symmetric for big omega. You have to use the definition of big O to know that there exists some constant and that you're dealing with a less than or equal to.